My name is Tyler Wiggins. I'm the product development manager here at Everest Solar Systems. I'm going to be talking to you guys today about a couple things. One, we're going to go over some basic guidelines for designing east-west racking systems. And then in the last half, the majority of the presentation will be using our design tool that Everest created called BaseOn, where we'll look at how to design east-west systems, specifically our Dome R² ballasted system. So go ahead and get started here. So the first thing that is I would say, critically important for designing any ballasted system is really understanding exactly what the requirements are for AHJ. So this can vary, at least in California, pretty dramatically from city to city. But you know, as far as California compared to other states, I would definitely say that California is more stringent on these. What's going to be important for us today, we're going to be looking at, is understanding exactly what's required, specifically fire codes or seismic designs, wind designs, anchoring, things like that. Another thing I wanted to make sure that I made clear today, and something to keep in mind, is that if you're designing an east-west system or ballasted system for a residential installation, that the AHJs will likely have different requirements for ballasted systems on residential than they would even on commercial. So something to keep in mind when designing these types of systems. One thing that I really wanted to go into detail today before we begin working on our designs is understanding what variables are affected with a ballasted system. So, you know, for the most part, there are 12 unique variables here related to both the building and the module, solar panel, as well as the design codes. And by these, I'm referring mostly to ASCE 705 or 710, along with the wind speed, snow loads, and the other variables associated with those design codes. So I'm just going to talk about briefly some of what I feel like are the more important variables. And we'll begin with the roof height. So with this variable, I definitely think more so than the others, it has a very large impact on the ballast or weight of the system, or how many anchors it needs, basically what the loads are from the wind on these systems. If you're designing a ballasted system and you're unsure of what the roof height is, I would strongly recommend making a best guess, definitely early on, to get a general idea at least of how much material or how heavy this system is going to be. Typically, if you're looking for best guess, if you know how many stories the building is, you can multiply that number by 12 feet. That'll get you in the range. Maybe that might be a little bit on the higher range, but it better be more conservative, I think, in this regard. The next variable that's critically important is the parapet height. So again, if this one is unknown, definitely a good idea to make a best guess. If you design a system with 0-foot parapet height and later find out it's 2 feet, it's absolutely going to change the ballast along the edges of the roof for those modules that are located near the edge. So it's definitely best early on to make a best guess here. Another one, edge distances and fire aisles. This one, again, is determined a lot by the AHJ. Each AHJ might have different requirements for what these fire aisles need to be. There are some rules of thumb you can use if it's unknown and you're trying to get an early estimate. Typically, if the building's less than 250 feet wide, so its longest wall is 250 feet wide or less, or sorry, 249 feet or less, be a 4-foot edge offset. If it's greater than 250 feet, a 6-foot edge offset is a good rule of thumb. And then there's one that not a lot of people are aware of, but one that's worth keeping in mind if you're designing a system for a larger building. For every 150 feet of an unbroken module array, you need an 8-foot fire aisle. So again, this one can be tricky, and it definitely would recommend looking at what this is specifically required in your jurisdiction, on what they consider unbroken module array or not. So something to keep in mind. Wind speed, this is another critical variable. I'll get into where to find this if it's unknown in the area that you're going to be designing the system in. We have a website you can use that will give the give that variable for you. Snow load is another important variable to consider, and I'll show you where to find that as well. Getting near the end here, building risk category. This one is not a common one that comes up. I would say the majority of the buildings I see solar systems going on are risk category 2, but this is definitely a critical variable if you're installing these systems on, say, a school or a government building. So I'll go over these briefly. Risk category 1 is one that I see very rarely. This would be like a barn or a storage shed. You probably would not see this very often with a ballasted system, but it might come up. Risk category 2 is standard business or house. This one I definitely say I'm seeing in 98% of these installations. Risk category 3 gets tricky. It's a school or a daycare, but if it doubles as a hurricane shelter, bomb shelter, or any other type of shelter, then it would be considered a risk category 4. So risk category 4 includes government buildings, hospitals, or if it's just a storm shelter and that's all it functions as, that's where it would also be category 4. So again, this one, most cases comes down to what the jurisdiction or the engineer of record considers the building to be. So if you're unsure, definitely recommend contacting them. It will make your design with regard to the materials required as accurate as possible, knowing this as early on as possible. Exposure category. This is probably the most difficult one to determine. I've definitely seen cases where it very clearly looks it would be an exposure B, but the AHJ requires an exposure C. So this is another one, if you're in doubt, checking with the AHJ. There are some rules of thumb, again, you can use if you're just trying to get an estimate early on for a bill of material. So if it's exposure B, this would be like a house in a neighborhood, or if it's a commercial building, it's surrounded on all 4 sides by other commercial buildings. Exposure C would be if it's like a farm or a building out in an open field. At least one side of the building doesn't have an obstruction for 1,500 feet. That would be considered exposure C. Although that one I would say is probably the most difficult one to determine if it's a B or a C. Exposure D is one you see rarely, but we have seen some installations that were considered exposure Ds. So this would be basically a building that has an open waterway. Very common to see this resort on a beach, or if it's a structure that's near a dock and the ocean is right there, might be considered an exposure D. But again, I've also seen buildings that were near harbors, and the AHJ considered them exposure B or exposure C. So again, the engineer of record or AHJ will have a better understanding of what this needs to be. I'm going to talk about some design guidelines, some good things to keep in mind when you're designing these ballasted east-west systems. So I would say the best thing to do right off the bat is just determine what your strategy is. So in the time I've spent designing these systems, I would say I've seen 2 main strategies. The first one is trying to maximize the module count on the roof, trying to fit as many modules as possible. And some things to keep in mind when you're doing this is one, are there weight restrictions? What are the allowances with regard to PSF on how much weight we can put on top of this roof, and then the second being, are there specific AHJ requirements for fire aisles and things like that? We want to make sure we're not putting too many modules on the roof to a point where there are modules where a fire aisle needs to be. So something to keep in mind when going down that particular road using that strategy. Second strategy I've seen, it goes along with the first one, where you're trying to get the most amount of modules you can, but you have a lot of limitations on system weight. So where this one comes up a lot is, that I see is common, is trying to fit as many modules on the roof as you can, but staying under 4 PSF and not being allowed to anchor. So that one gets pretty tricky, where we really need to consider the location of where we are installing the PV, and also taking into account the fact that we need to hit a certain minimum with modules and not being allowed to anchor. So that one gets a little tricky. And we'll go over some steps we can take to accommodate for that. If neither of the above, definitely would recommend design with stringing in mind. We'll go over that in a little more detail when we get into our designs. For considering design guidelines with ballasted systems, there's some basic rules for lower ballast. Larger subarrays typically equals lower ballast. So with our system, really take module sharing into account. And what I mean by this is that when we're looking at arrays, if they have, say, 20 modules on them versus 6, the array that has 20 modules on it is taking into account the weight of the racking and the weight of the modules when it considers how much ballast it needs. The same can be said for the 6 module array, but because there's only 6 modules on there, it's not as much weight to begin with without adding ballast to it. So using that weight sharing can definitely be helpful. So keep your subarrays as large as possible to keep your ballast as low as possible. Another good guideline for ballast is subarrays located in the middle of the roof will typically have less ballast than those located on the edges. So really this comes down to the roof zones, which we'll get into. Designing near the middle of the roof will, in most cases, lead to less ballast than designing systems where located on the edge of the roof or near the edge of the roof. So I'm going to get into some examples using BaseOn. For those unfamiliar, who may be unfamiliar with BaseOn, it is our design tool that we have located on our website. So this is the main page of our website here. The BaseOn tool can be located here under your project. BaseOn D Dome R² design tool here, and then this button directly to BaseOn. So for those who do not have an account, there will be a sign up button located where my name is here. So you'd want to click that, fill out your information, and I will be able to give you an account. So I'm going to jump right into this. Again, trying to be cognizant of everyone's time here. If I go over, please note that this webinar is recorded, so be able to view it at a later date. A quick thing I want to go over right off the bat, if you get stuck or have any questions about something specific to BaseOn, we do have a help feature which is located at the top of the screen here. And there'll be a list of frequently asked questions, those types of things, to help you out with some of the design variables. So I'm going to get started here. I found a roof that I think will be a good example for us to use today to design a system on. It is located in Vernon, California. It's this roof here. So I haven't actually been to this site, so I'm not sure about these sections here and here, so I'm not going to build on them. They do appear to be sloped to me. So we will consider our allowable area for modules to be in this region right here. So to save time, I'm not going to fill out the information here, but this is where we'd fill out the project name. An important thing is the design method. I know for California, it's going to be ASCE 710, so I'll leave that where it is. I'll go to my roof tab next and begin drawing my roof. So I'll click this plus button here. I know that this is a flat roof. This one is rectangular, so I'm going to go with rectangle, and then it's flat. Add. So I'll zoom in I'm going to click on the corner. This is an important thing to know. You definitely want to click on the outside of the building wall, not the inside of the parapet here. Click there. There, we'll bring this down. If I use the center click button, I can drag. Then I'll zoom in here, right on the outside, and I'll click again once it turns green, and then it's done. So some important things to know, those variables we talked about before. Building height. Again, I haven't been to this job site, so I'm going to have to use my best estimate here. For these commercial buildings, they're typically anywhere from 20 to 40 feet. I'm going to go with 30 feet for this one. It looks like it might be lower than that, but it's difficult to tell from this angle, so I'm going to go with 30 feet. Roof pitch. Some important things to note on roof pitch. The system cannot be installed on a building that has a roof pitch greater than 5 degrees. So with this one, I'm just going to assume that it's 0. Parapet wall height. I don't see any shading. If there is, it might be minimal. But since I don't know, I'm going to go ahead and put 1 foot in there. There very well could be a parapet. So I think it's best just to be conservative at this point. I'll assume that there's a parapet there. Coefficient of friction. With this one, certain jurisdictions require a testing for this, which we do have. It's located on our website. For this example, I'm going to assume it's 0.5, but we do have that located on our website. Obstructions. So adding them, we have 3 options. We can draw a polygon tool, which I'll start, or a polygon shaped, I should say, obstruction. I'll start off with that. I have a, looks like what maybe a AC unit here. So I will draw this in here. You'll notice that it's snapping at 90 degrees and 45. If I press and hold the shift button, I can now put a more custom angle in there. So I know I don't want to build anywhere near this thing. So I'll make it like that. It's green. I'm going to click again. And now it's done. I don't want to be anywhere near this obstruction, so I'm going to set an offset of 3 feet for right now. That looks pretty good. Another obstruction tool we have is the line tool. Click right here. Right there, it's green. I will click again. I will now add an offset. I don't want to be anywhere near, it looks like conduit or something like that. I'm going to go ahead and put a 2-foot offset off that. Okay. I have another obstruction here. I'm not sure what that is. I will add a 3-foot offset on that one. Okay. Again, I'm not sure if this area is sloped or not. I'm going to go ahead and just create an obstruction there. That way the tool will not allow any modules to be placed into that area. I'll do the same down here using the square. There it is. Okay. Next, I'm going to add the skylights. So the easiest thing to do when you have obstructions that look the same like this one is, one, I want to first add in my offsets right off the bat. After I built the first one, I'll go with a 2-foot offset off these. I can then hit this button here, the duplicate button, and it will duplicate the obstructions for me. So I think I have 8. Let's see. You can then click, highlight it, click and drag, and move the obstruction to where it needs to be. There's that one there. Couple more. There, nearly done. Almost there. Okay, looks like I have one more. Duplicate, drag, okay. I'm not sure what this is. I'm just going to assume that they're not obstructions for now. Again, I haven't been to this building site. I'm not sure. I haven't verified that. So we'll just assume we can build on it just for this example. So at this point in time, I have, at least what I can tell, all of the obstructions accounted for. I believe at this point I'm ready to add modules. So I'll come over here to design. You have two options for adding modules in. We have a list of some common ones, although because module manufacturers are coming out with modules so quickly, it's difficult to keep as up to date as possible with this, but we update it as often as we can. If we do not have the module, you can always click user defined and add it manually. So for this example, I will just continue with the default Axitech module. I will then go into module arrays by clicking here. And then I will click this plus button. I'll click D Dome R². And I have two options for adding modules. I can click on module field, or I can click on complete roof. So I'll start with module field just to show you how that works. Click here. So with module field, it's basically like drawing that square roof. It's just adding a square of modules in, or a rectangle, I should say, of modules in. You click again once it turns green, and it adds the modules in. For this example, that would take a very long time to add them in by hand like that. You can do that. The option I prefer is filling the roof in. Now that we have all of these obstructions in, it will be a lot easier to fill the roof. So we'll click on complete roof, D Dome R², complete roof, and then we'll click on add. It's going to take a second, and there it is. So as you will see, it's defaulting the edge distance to 1.7 feet. Now we know for this commercial roof, especially in California, 1.7 foot edge distance is not going to work. I do get questions sometimes about why it defaults to that. Per our system, per our wind tunnel testing, that is the absolute minimum that you could possibly have. So there are some jurisdictions for residential installations of ballasted systems that they may only have a 6-inch or a 1-foot edge distance requirement. So you could, theoretically, for certain jurisdictions, get it as close as 1.7 feet. But we know that this isn't going to work out for this. So this building dimensions, if I click on this button here, it's on obstructions for roof. With this button here, show dimensions, it's 241.6 feet. We're pretty close to 250 there. We could probably get away with a 4-foot edge distance offset, but for the sake of this example, I will just do a 6-foot just to be safe. Let's put in my 6-foot edge distance there. So it's measuring out 6 feet from the edge of the roof to what it considers the edge of the module field, which is this blue line here. So really, we're definitely being conservative here. We have some space. Again, one thing to note is that we're going off of a Google Maps imagery here. So these distances are really best estimates. If there are concerns about fitting modules on the roof, the best thing you could do is one, go up there and physically measure the roof, or if you have AutoCAD available to you. One thing Everest could provide is module blocks to you, and you could measure out the modules to make sure that, and AutoCAD to make sure that they actually fit. So again, I feel like we're being conservative here with the distances, so I'm feeling pretty confident that I'm going to be able to fit the modules going in this direction here. So some things to look at here as far as strategies go. If my goal is to absolutely fit as many modules as possible on this roof, I definitely see some areas I could, improve upon. I could likely fit some more modules right here. We're getting pretty close to this obstruction, but it looks like there may be room. Again, going up there and physically measuring it would be a helpful approach, but I could fit more. Some other things I'm noticing is I have some smaller arrays located near the corners and edges of the roof. I do think these are going to be heavier, and we'll get into the results page in a moment, and I will show you that they very likely will be heavier here than the modules located near the center of the roof here. So One of the main things about our system and about this BaseOn tool that confuses people who are new to it is the customizability, that's a word, the ability to customize where the thermal brakes go. So when I'm talking about thermal brakes, I'm talking about these brakes you can see between the modules here and here, almost like longitude and latitude lines on a map. So the reason these are put in, for people who may not know, is that because this system's made of primarily aluminum racking, and the aluminum modules, they will move when they're heated up. It's very slight movements, but over long enough distances, as we could see here, we could see some, potentially some shifting of modules if we were to run maybe like a 300-foot subarray. So it's something we wanted to take into account. So we require thermal brakes every 50 feet. So those thermal gaps or thermal brakes can be customized using this function here. So some things to keep in mind. The more thermal brakes you have, the more material the system will require. So let's think about this for a second. I'll look at first these thermal brakes running in this direction here. So where this thermal brake, so the thermal brake is where this white line is, and the red lines are where there's no brakes currently. So where this red line is, these module pairs are sharing components along this red line. Where I have the thermal brake, now these module pairs are no longer sharing components. So if I was to say just put a thermal brake in here, just because, I now am doubling the components required along this line. So a thing to keep in mind, the more thermal brakes you have, the more material you're going to have. So we definitely want to keep this as minimized as possible. Now, there's another thing to consider too with placing thermal brakes is the ease of installation. So I'm going to take this off for a minute to make it easier to show. This array is not a nice rectangular shape. It's kind of like a, almost looks like a cooking pot shape with a handle right here. So constructing this array is going to be slightly more challenging than constructing an array that's a nice rectangle like this. So with moving around and customizing where we have our thermal brakes are, there's a couple benefits. One, we can design it so it's easier to install. Another thing is we can design it so it has minimized material. And then a third thing is, getting back to our ballast, is placing our thermal brakes that make the system as light as possible. If we look at this array down here, it is nice that it's rectangular, but it is also near the corner of the roof. So this array is going to have higher ballast than, say, this array. If we add more weight to the array in terms of panels, so if we make this array larger now, we now have the possibility of reducing ballast in this corner, effectively reducing the weight on the roof, hopefully reducing material count, in essence, reducing the cost, the overall cost of the system. So in editing thermal brakes, the first thing I like to do is just create a thermal brake at the very bottom, even though one isn't required right here because there's obviously no panels over here. It just creates a nice starting point. So to create a thermal brake, you click on the line that you want the thermal brake and you hit brake present. It's going to recalculate and it puts in that brake for us. I don't like the shape of this array where it is with that line right there, so I'm going to try and go up to here, which I believe I'll be able to do without going over my 50-foot allowance. Okay, I was able to do that. So now if we look at the array now, it's now in a much easier shape to install. It's also larger, which is good. That's what we were looking for. Again, right here, am I able to go here? I believe I will. I want to make this a little bit easier of a shape to install. See if we can remove this thermal brake here. We are able to do that. Okay. I like the shape of that array. I like the shape of that array, and I like the shape of these arrays. So looking pretty good at this point here. But there is one thing I haven't considered yet, and that is our fire aisle. It looks like this is likely going, this unbroken array here is likely going to be over 150 feet. So how do you know where the 150-foot break is? The easiest thing to do is to come back to our obstruction tool and grab a line. We're able to draw a line. We can measure it out to 150 feet. Go about right there. And now we know if we come back to our design tab, we know that that white line is about 150 feet, so we would need a fire aisle right there. I like to keep my fire aisles in the middle of the roof. I just like the way it looks better. Again, this is another opportunity to be specific about where we want to basically break our modules, where would be if I'm trying to maximize my module count, I want to be specific about where I'm putting that fire aisle in. If I put it in, say, right here, I have to remove a lot of modules along this line here. Whereas if I put it here, I may not be losing as much. It's hard to tell. It can get tricky depending on where your obstructions fall. So I'm going to go ahead and put it in right here. I think that's a good place for it. To do that, use the eraser tool, which is located right here. So I have a couple methods for erasing modules. You can click them and it'll delete the pair. You can also press and hold the control button and that will delete an entire row. You press and hold control, you can bring it right back. If you press and hold shift and click, you can delete an entire column. We're not going to do that in this case, but we'll go with the row. Here it is. So I know that these modules are around 5.5 feet. If I'm looking for an 8-foot fire aisle, I know that that isn't going to be enough. So again, what I can do is customize my thermal break, and I can come in here and get the extra 2.5 feet I need. So I'll go ahead and make this 36 inches, again, just to be conservative. So I now have a 36-inch break right here, so we can see, along with deleting that module row here. And there's my fire aisle. Again, certain jurisdictions don't allow an obstruction between the fire aisle, but I have seen some that do, but they have requirements on how far this gap needs to be. It really is just specific with the jurisdiction. So again, it's something to keep in mind, figure out what their requirements are. Typically it's unbroken, so this may not work. And if that's the case, we're still okay here, because what I can do is click on the eraser button, come back and click control here. I can control click down here, and now I have an unobstructed fire aisle path right here. So that'll work out for me. Okay, so now I have my fire aisle path in. I don't need one going in this direction. It's only 135 feet across here, so we're going to be okay. I'm feeling pretty good about this. So come into loads. Really quickly go over this. Sorry guys, now we're going over time a little bit here. Again, for anyone who joined recently, this webinar is being recorded. So if you need to leave, we'll make sure you get this webinar. To get wind speed, if it's unknown, you can click on this button here. It'll take you to this website. You can punch in the address and it will give you the wind speed. To save time, I'm going to assume it's 110. I know it's pretty consistent with that area. It's either 110 or 115. Snow load, I know there's no snow load in this area, but again, there's a link here. You can click. It's very similar to this one. It'll punch in the address and it'll give you the snow load, but I know it's 0 in this case. So next I'll go into the results tab at the top. And now it's calculating our ballast requirement, and it's done. So I can zoom in here. So another common question I get, and I apologize there's no legend on this, something we're trying to add. What do these numbers mean? So the 735 is basically an index number. It's a way to keep track of what module pair we're talking about. So this is module pair 735. And module pair 735 requires 7 ballast blocks right here. That's what that 7 means. 7 ballast blocks here and 0 anchors. So that one definitely seems a little high, and we can look and see what the reasoning is for that. So because I've been designing these systems for a couple years now, I know what it is. Has to do with 3 things here. One is it's a small array, so there's not a lot of weight sharing going on. And 2, it is located near the corner and edge of the roof, so it's going to be having higher ballast there. A way to see that, specifically what areas are going to require more ballast, you can do that by clicking this button in the top right corner and then clicking on roof zones. So these zones aren't labeled, but a good rule of thumb is stay out of the blue area and stay out of the green as much as you can. But we can clearly see here that this small array that doesn't have a lot of sharing falls right in a corner zone, which is why it has high ballast compared to this array here where we see a lot of zeros. No ballast at all required in many of these pairs. So overall, the system is very light. You know, I would say it's coming in at only 3 PSF, so it's very, very light. We do have some areas where we have a maximum pressure of 8.65 PSF. It's probably going to be in the corner. Could very well be this pair. Looks like it is. So you know, overall, we're coming in pretty light. So again, when I was talking about in the first half of this presentation was loading variables. I assumed for this one we were at wind exposure B. It is completely surrounded by other buildings, as we can see here. But let's say, just for the sake of this example, that the AHJ required this to be C. And for the sake of this example, let's say that the building owner or whoever is requiring the weight of the system be under 4 PSF. Okay, so as we can see, changing it to exposure C raised the ballast a lot in this corner here, as well as along the edges here and here. So if I come into system details here, I can now see that the average uplift pressure is greater than 4.24 PSF. So I know that's not going to work. Let's say that we were allowed to use anchors. We can now optimize the system to form what we would call a hybrid system, to where it's using block and anchors. So we can click the Use Anchors button, choose between 2 anchors. I'll go with an eco just because. I can now click on the Limit Downward Pressure button, and now I can give an acceptable downward pressure. So this is referring to the max downward pressure, so I'm just going to start with 10 right off the bat. So what I like to do in this instance is I try and limit the amount of penetrations that we have into the roof. A way to do that is you can uncheck the Use Anchor button. And what this is telling us, where it's red, is it's saying you've limited us to 10 PSF, but we have to add more block or more ballast into there that makes that pair greater than 10 PSF. So now what I know is that every red pair is where I'm going to need an anchor, which makes sense right in the corner. Those are our heaviest pairs. So at this point, what I like to do is come into system details here. After I click anchor, all right, click anchor. Come into system details here and see how much that's affected my system. So we're still greater than 4.4 PSF. So I'm going to bring this back down again. And basically what I can do is really dial that in to get me to where I need to be. So to get below 4 PSF for an exposure C with the conditions we have, it would definitely require a lot limiting and using more anchors. But if that's not the case, another option you could do, if you have the ability to remove modules, let's say, you could remove modules in areas that require more ballast. So here and here. Another thing we could try doing is moving that thermal brake from here. Maybe we could try moving it down to here if it's possible, make these arrays a little bit larger. So we take sharing, more module sharing into account. That may help us out. But typically when you get into the exposure C or very high roof heights areas, it can be more difficult to reduce the weight of the system without having to go to anchors. But again, going back to our rules of thumb, the larger the arrays we have, the like this array here, typically the lower ballast you will see with regard to how many blocks you need under a specific pair. Another rule of thumb, designing towards the inside of the building as opposed to the edges. As you can see right here, we have zeros and ones, whereas right here we have threes and zeros. Require more ballast, more material to hold that ballast. So those are some things to keep in mind. As far as summary goes, there are some options you have. There's the bill of material. You can locate it here. So again, if I'm trying to design for lower bill of material, I will constantly be looking back and forth here between my design, removing modules, changing my thermal brakes to see how I can reduce the amount of material I have. With this system, definitely the lower ballast block count that you have, you are going to see a more reduction in material. And once that's done, once you have the system how you'd like, you can generate your report. So bring that up right now. Go over that quickly. Sorry, I know we're going over time a little bit today. Have our report here. So in this report, it tells us a lot of things. I won't go through everything just to save time, but it has our project data. It has our system, and it has the locations of where those, we'll zoom in a little bit here so we can see that better, a location of where those modules are located with regard to the edge of the roof, and the size of the subarrays, where some of the components are located, things like that. It also has our ballast plan, so we can see here, showing us exactly where the ballast needs to go. It also has at the very bottom our bill of material here. So sorry again for going over time today. There was a lot to cover. I covered as much as I thought was some of the key important parts for designing these east-west systems. I'm now going to open it up to questions. We have a user interface. You can put your questions in at that point, and that now would be a good time. Looks like I have a question in here. Okay, it says, how much down pressure the roof can withstand? How can we know this? Okay, I'm assuming that question is referring specifically to the building. So are you asking, it sounds like what you're asking is how do you know what the maximum allowable PSF is for the roof? That's really going to be determined, I've seen it determined by a couple different people. So it could be the engineer of record. If the engineer has looked at seismic design criteria or looked at how much the roof can withstand, they will typically tell you, okay, this has a maximum of 5 PSF or this has a maximum of 4 PSF. That's typically where you see it the most. In some cases, though, I have seen the building owner have a specific requirement for how much weight they'd like on the system. In that case, usually the building owner also has some sort of engineering background, and they've made a requirement for that. But in most cases, I would say 99% of the time it's the engineer of record. They'll tell you. So going through some more of the questions here. Oh, looks like I have a good amount. Okay. Can we use the tool with Mexico sites? Yes, you can. We do have an engineering team in Mexico who uses this system for designing systems in Mexico. There are some things to keep in mind with that. One is design codes. So this is specific to ASCE 710 and 705. For your wind speeds, you'll need to convert them to an applicable 710 or 705. There are conversion factors. You can look them up online. Another thing that might be helpful is we have languages, different languages for different countries in here. We also have metric or imperial units. So if you'd like to do this in meters, have that option as well, metric or imperial. Another question I got, I wanted to address real fast while I'm talking about the tools at the top is saving. Don't forget to save your project. Hit this button up here. There's also a way, if you have a project file that you would like someone from Everest to look at, you can click the download project file button and email us the project file and we can help you out with that. Okay, next question. Can you have different edge distances for different sides? That's a great question. Okay, I see what you're saying. You want to have it closer on one side than you do on another. Right now, we don't have that function, but I will add that to the list of possible functions for the future. What I would recommend doing is what I did here, where I drew an obstruction with using a box. Let's say, for example, well, I mean, I guess this would be a good example here. I wanted to have a different edge distance here. I just drew in that box at you could you know, specify how long this is. This is a 18-foot box here, but let's say it needed to be 25 feet. I could make it 25 foot long. So that would be, I guess, a quick way to get around that. But I will add that to possible features for the future. Next question. How close to the edge do you need to get for the rectangle roof? How close to the edge do you need to get for the rectangle roof? Oh, I'm guessing that question is how close do you need to draw the roof to, I'm assuming this question is referring to how close do I need to make this red line to where the edge falls. Again, what can be difficult with this is that we're going off of a GPS image here. So I think it comes down to what the base of this question. If you're referring to how close you need to get to make sure that we fit the modules on the roof, the absolutely best way to do that would be to go up, measure the roof, or if you have an as-built drawing from AutoCAD, you could measure it out and see. But if you're talking about drawing it on the roof edge here, the system does not recognize where the edges of these roofs are. I could draw a roof, just to give you an idea, I could draw a roof wherever I want on this. Let's say that there was going to be a new construction right here. I could just click and draw. The system doesn't have any recognition software for where the edge is here. So to answer that question, I would say draw it the best that you can. That will give you the most accurate readout for ballasts, edge distances, things like that. Okay, next question. Looks like I answered that one. The question says, I suppose you are using this as an example only as you seem to have shaded two parts of the roof that are tilted. Yes, so I was trying to find an example that didn't have too many obstructions on it to save us some time. I was unsure if this area was sloped or not. It looks like it is from this image, but it's unclear. But the example also shows you that you have the ability basically to block out an entire section of the roof. So there are some examples where they might have say it's like a large AC unit or something that shades a large section of the roof. So you could, it is another way to show that you could block out a section of the roof. See, okay, great. Okay. Okay, I have another question here. The ballast blocks are a special type of block or just construction cinder blocks? Great question. So this system is specified for a paver that is 4 inches by 8 inches by 16 inches. Now, you do not just have to use that specific paver. We've seen people use 16-pound blocks that had similar dimensions. What's important is that, I'll bring up a picture to show you, is that the paver fits in the ballast tray. So there are requirements as far as the paver that will fit. Let's see if I can zoom in here. As you can see, the pavers run along from peak to peak right here. They are 8 inches wide in that direction. If we were placing ballast over the corner strut components, they would be 16 inches wide in that direction. Again, another thing to keep in mind about the block that you're going to use, definitely you'd want to make sure the block can handle the environment that it's in. Some pavers or blocks perform better in certain environments than others. For example, some pavers cannot handle ice very well and snow very well, so something to keep in mind for that. But yes, there are some dimensional requirements for the block. Another thing to note with this is that, let's say I wanted to use a 16-pound block versus a 32. I know that it would fit. I could come in here and change this to 16-pound block. And the system is now going to account for that and calculate for that. So you do have that option. Look at the next question here. The wind speeds for Mexico have to be manually entered. Yeah, so the wind speeds for whether it's for the US or for Mexico, they still have to be manually entered. We would enter that right here. So let's say the wind speed was 127. Some areas of the United States have that. I would enter it right there. It would be the same thing for Mexico, but something to keep in mind is that if I'm looking at the design code for Mexico, which I know at least recently I looked at it, it's off of a 50-year return. That wind speed is going to be different for ASCE 710, which is based off a higher return than it is for Mexico's wind return. So you would really want to make sure that when you enter the wind speed, that it is the equivalent for either ASCE 710 or ASCE 705. And there's some literature online that you could look up to see what's the best way to convert that. Another good person to ask at Everest is, his name is Ernesto. He's located at our offices in Guadalajara in Mexico, and you can contact him on our website. I believe it's Everest-Solar-Systems.mx, I believe. And you can get his contact information from there, and you can speak with him, and he'll have some better information with regard to converting wind speeds from Mexico's to the applicable code for using this system. Another question here. What about wind in hurricane-prone areas? We are on the coast of the Gulf of Mexico, 5 hours south of Brownsville, Texas. Yes, so that's a good thing to note. So we'll look at a very quick example here. I'm just going to delete everything I have just to show you how higher wind speeds will affect this. I'm just going to add a small array in the center of the roof. So There's no limitation with regard to installing the system in hurricane areas. I'll say that right off the bat. However, when you install in higher wind zone areas, there are a lot more things to consider with the design. For example, I'm just going to show what we previously had, 110 miles an hour. We'll look at the results. The loading on this, oh sorry, we're still in exposure C. I'm gonna go back to B. The loading on this at the center of the roof is very low. Don't need a lot of pavers here. What I'm seeing on system detail, the downward pressure max is 2.84. The upward pressure on the module, uplift pressure here on the module, 2.84. Not very high. The module can definitely withstand those types of forces. Now, if we come in here in loads and change this up to hurricane wind speed, which will be around 200 miles an hour, depending on where we're at, we now have significantly more loading on this system. Now, luckily, we're in the center of the roof here, but even so, we're seeing we need 14 pavers or 14 ballast blocks under here. The uplift pressure on our module is getting not too high, 9.4, not too high, but some modules like 72 cells can only handle 20 PSF going up. Luckily, we're still in the middle of the roof here. If we were to move this to the edge, which I will do right now just for the sake of this example, it's now, what it's showing us is it's not even possible to install in those areas because the load's just too high. So to answer your question, it is possible to install in those areas. There are a lot more considerations to make though, and the variables that go into designing the system are going to be more critically important. I mean, it's always critically important, but I guess what I'm trying to say is that now you have to think about things like what's the maximum loading the module can withstand. Whereas before, that may not have been as much of a consideration, especially for areas like Los Angeles, California, where we're not getting any hurricanes. So something to keep in mind. Just more variables to consider. Okay. Any more questions? Okay, I have another question here. When you say paver, I am to assume that they are solid blocks, right? Yes, I'm talking about a for that paver, it is a solid block that is 4x8 by 16 solid block. And I have seen those come in as 4x8 by 16 blocks, but they're 16 pounds. And I've also seen them come in at 32 pounds, that's the standard one that we recommend for installations. So 32-pound block, that's 4x8 by 16. Another question. You could use Street View to determine building height. Yes, you could. It's great. That's definitely something you could do. I would recommend doing that if you're trying to get best estimate. The absolute best thing you could do to be the most accurate is if you could go measure it. But yes, estimating Street View, would definitely recommend doing that. It's a great call. Okay, that looks like that's all of our questions for today. This was definitely one of our more popular webinars. I think we're going to hold another one in a couple weeks, maybe go over some more advanced topics or cover things like shading. Was not able to cover that today. Do have a shading feature on here. And stringing is another thing we did not go over today, designing for stringing. We can do that as well at another time. So if you have any questions about this specifically, that you'd like me to answer, please feel free to email me. My email is t as in Tyler .wiggins, WIGGINS. That's at Everest-SolarSystems.com. Be happy to answer any of your questions. You can also email us in at info@Everest-SolarSystems.com. Another place to get some help with this. If anyone has any further questions, now would be a good time. Thank you very much. I hope everyone has a great rest of the week and a good weekend.